So just perusing Slashdot, and NVIDIA-powered neural network produces freakishly natural fake human photos. Looked at the video. Check out these fake human photos. Wow, right? I mean, are those fake? Most people don't have foreheads that blend into the background, so I kind of want to believe that's generated by a neural network. First thing I see is, hey, generative adversarial network again. And we just read a paper about that. So I figure I should call this to your attention. Now, I haven't had a chance to look into this yet. I have no idea if it's totally legitimate or if it's just kind of fakey. What would be the biggest flaw in this paper? Suppose that it turns out this is not as awesome as we're assuming. Why? What did they do wrong? How would you know? Yeah.
Or are they doing like super resolution?
Okay, yeah, so I don't know. NVIDIA neural network generates photorealistic faces with disturbing natural results. I haven't read the paper yet. I can't tell you. The one test that I think would really tell it is to ask the question, what is the closest image to each of these faces in their training data? So I really hope as soon as we open the paper, we'll find a table that shows here's some generated images and here's the closest, the k nearest neighbors of these pictures in our training data. And if they've got that and the nearest face to that guy is not in the training data, then holy cow, they have nailed the manifold of natural photo faces. On the other hand, if every single one of these pictures has a corresponding point in the training data, then we assume that they just overfit the training data and you couldn't actually generate a face that's not in the training data, right? Okay, but at least as far as tricking the human mind, I'm just going to say every one of these faces was machine rendered. That's pretty darn impressive. Should we watch the video real fast? See what it says? Okay. Progressive growing of GANs for improved quality, stability, and variation. I don't know how to turn on audio here. I should probably pause my recording so I'm not stealing somebody else's video. So let's talk about distributions. We just saw fitting to a manifold, and another way to describe that is they've essentially modeled the distribution of faces. So think for a minute, what is the relationship between distributions and manifolds? What's a probability distribution? So we usually draw them kind of like this. We make crosshairs and we do one of these types of things. Yeah, we usually say distribution sum to 1. We're usually doing statistics or probability theory when we talk about distributions. Whereas if we have manifolds, we're usually drawing a funny shape in high dimensional space, and we're saying, hey, there's a bunch of points sampling this space and we're trying to fit to it. So if we had a multivariate distribution of faces, it's probably going to be more like this, right? With a whole bunch of them in the center and not so many way out there. And if we were to fit to this manifold, our training data would ensure that we fit in this region really, really, really well. And in these regions, we'd kind of reach out for whatever points we happen to have, but otherwise let it drift because we don't care so much about those, right? So to some extent, manifold learning tries to be really accurate here, where there's a lot of training samples, and doesn't care so much over here because it's trying to minimize sum squared error. With a distribution, you're kind of assuming you're accurate everywhere because we're working with probabilities. And let's see what else is there. Do you see that essentially any region in the probability space is sort of equivalent to measuring the density in the manifold space? Yeah. So there's sort of if you were to take a point and find its k nearest neighbors and measure the distance to the k nearest neighbors, average them or something like that, and suppose you took 1 over distance, averaged over the k. Let's call that expected neighbor distance. Uh-oh, that made a word. Well, pretend that E of ND means you take the k nearest neighbors, you average the distances to them. So it's the expected neighbor distance. You take 1 divided by that. Do you see that's the density in the local region, or it's an estimate of the density in the local region. And you see that that estimate of density is kind of the same thing that's happening in a probability distribution. We're saying, suppose you have a whole bunch of values, how dense are they at any given point, right? Okay, the difference is a probability distribution is, we usually think of as being univariate, right? But this certainly could be multivariate, in which case we've got, too hard to draw in paint, but here's sort of a multivariate Gaussian distribution. I got to draw a really big one now because around here there's a lot of density, but the farther out you go, it's less dense. Now we've got a surface. And in truth, any surface you've got, as long as you divide by its integration such that it sums to 1, you could call a probability distribution if you wanted to, right? Okay, so there is a strong relationship between the two concepts. There are also some differences. Important to think about the difference. To a large extent, if you can model the distribution of some data, you are learning the manifold. You're fitting to the data. And so they're kind of almost the same thing. Okay. Some other properties of distributions I want to point out before we get into the lecture, because I just want to make sure you know what we're talking about.
So if you're modeling the distribution, though, all you're getting out is probabilities. Right? Because
yes.
Whereas if you're modeling the manifold, you're actually getting out the stuff that is in the manifold.
Okay.
Right?
Yeah. To some extent, I want to say, what's the difference?
One's a number. One could be a picture or a car, or it could be something.
Yeah. Well, you're making the assumption the distribution is univariate. This distribution is univariate. Suppose then we take we refer to the distribution of faces.
Yeah.
What is the likelihood of this face? And I pull some random face out that you've never seen before. The probability of that face is going to be, well, probably 0, right? Assuming it's a generated face, because there will be 0 people on planet Earth that exactly match that face. For that matter, consider normal distribution. What is the probability? We'll take the standard normal distribution. That's the red one here. What's the probability from this red distribution that I'm going to draw the number 0 from it? Yeah, don't look at this and say, oh, it's about 0.4. It's not. There is 0 probability I will draw the number 0. But there is some probability I'll draw a value between negative 0.00001 and 0.00001. And in fact, it's probably 0.00002 times 0.4, if I did that right on the fly. So the true probability of every point in this space is 0. Don't get this mixed up with a categorical distribution where you say okay, so pretend this is 1 and this is 0, and these values are A, B, C, D, E, F, G, H, I, and J. And by I mean IUI. Oi. Okay, what is the probability of drawing an E from this distribution? About 0.4-ish is what I meant to do, right? And the probability of drawing a D is about 0.15 or something like that. In this case, there actually are probabilities of drawing each of these because on the horizontal axis, they take up space. If we go into continuous land, there is no probability of drawing any of these values. So if you were to draw the categorical equivalent of a normal distribution, it would look like this. Straight line is 0. The probability of everything is 0. But of course, that's hard to visualize. So what we do is we say, well, which 0 is bigger than the other zeros? Turns out this 0 is several times bigger than that 0. And so And of course that makes no sense. So we're talking about in the limit as you get really darn close to 0. But the point is the ratio between this one is bigger than that one. So if we multiply them by infinity such that these values integrate to 1, then this is what you get. Okay, so this is not a probability. Often people call it a likelihood. I think the official term is probability density. So the density of probability at 0 happens to be 0.4, which is not the same thing as probability. You okay with that? All right. Nevertheless, with that exception, with the caveat that we're off by a factor of infinity, this distribution behaves exactly like a categorical distribution. Okay, so let me ask a question to see if you understand categorical distributions, and this is a simple one. You flip a coin, you flip another coin. What are the odds that they're both heads? Assuming they're both exactly 50-50 equally weighted coins. It's an easy math problem. Come on, work with me. Show me you're awake. 0.25. How did you get that number? You multiplied. Suppose you have two 20-sided dice. What are the odds? You're going to roll them, and they're both going to be the number 17. 1 over 400, right? Yeah. Whatever the 20 times 20 is, the reciprocal of that is the answer. Okay, so if you want to know the probability that two things both occur, you simply multiply them. That gets you the joint distribution. A joint distribution refers, the term joint means both of them. Doesn't have anything to do with a hinge, but at a hinge there's two things, and so joint means both parts together. So the joint distribution refers to the probability that two things both happen at the same time. And now, having given all of that background, let's go to our Kalman filter problem, number 6. And I have no good pictures here. Now let me open the one here. By the way, I tried debugging it and figuring out why that top line is blinking. Cannot find it. I've convinced myself that the issue is caused by a bug in the SDL library and not in my code, in which case can't be debugged. So, well, can, but not without great difficulty. So I'm not going to worry about it. For right now, sorry that the graphics are imperfect. So here's what you know. You know that, okay, suppose you're in this state, and then something happens. I press the left arrow, and I go here. Now I ask the question, what state am I in? How do you solve this problem? Or how would you solve this problem?
Well, what are we given as input?
You know two things. You know you were here. You know what you did. You went to the left. I guess this is 3 things. And you have this new picture. So let me draw it out like this.
You know you are here. What is that knowledge?
Here's the thing we're trying to get at. We want state. The Kalman filter is all about estimating the state. And this is kind of an important problem that's near and dear to my heart because, in my opinion, the core of intelligence is understanding the world. I feel like if I get it, if I know what's really going on around me, if I understand and perceive, and if reality is not just around me, but it's in my head, I feel like intelligence is occurring. Because not only do I understand what things are, I understand how they behave, what will happen if I do these actions, then I know what actions to perform. I can correctly anticipate what I'm going to see if I have good state. So, to me, if you can estimate state, that's an important problem of artificial intelligence. The Kalman filter is a technique for estimating state. And here's what it says. Let's assume you have these two models. Okay, one of these we'll call the transition function, or the dynamics model, or we'll stick with those, state transition function. And this one we'll call I'll make them colors. Blue is transition function, yellow is the observation function. It maps between state and observation. Suppose you have those. Now, how are you going to estimate the state in general? What's your general approach for keeping track of what's going on in the world? I guess we're all just worried about figuring out what the heck is he getting at, and that's kind of, I don't want you to be thinking that, I want you to be thinking about the problem. But here's what I'm getting at. There's conflicting information. There's two ways to get at the state. If you look at your observations, you can say, oh look, I see a tiger in front of me, therefore there must be a tiger in front of me, and you can update your state to match the observations. By contrast, you could say, just a minute ago, I knew I was standing on the outside of the tiger cage, and then I jumped over the wall. Based on this, I compute I must be inside of a tiger cage. Now, if we put these two things together, that works out quite nicely because, hey, you're at the zoo, there is a tiger in front of you, you're going to die. We have correctly estimated our state that matches both the actions in the previous state mapping forward to our current state, and we've inferred from our observations that is in fact a tiger, not something else. On the other hand, let's see. Funny quote from Zoolander. I better not do that one. I don't know. Let's see, he was climbing what was it, Kilimanjaro, and suddenly he was falling, and he said, wait a minute, I've never been to Mount Kilimanjaro, but I have been smoking peyote for 2 weeks straight. So what happens when they disagree? You are here at this blue dot. This is true knowledge. When you are at that state, you see that observation. Well then, you get a new observation, which looks kind of like this. I'll make a blue dot right there. Okay, it's not a very good one, but pretend that, based on this observation, if you calculate backwards, you compute that you are right here. And you think to yourself, what did I do? Oh yeah, I pressed the right arrow, which moves myself to the right, and based on that, I compute that I am right here. So now in your head, you think to yourself, I know I'm right here. Oh wait, but I also know I'm right there. Which do I know? What's the truth? How do you resolve to what is actually the state of the world, given that you have both observations and this knowledge of how the world works and this memory of what you did? Simple answer, obviously, is to say, well, let's just average between the two and believe that we're right here until we know otherwise. And if we do that, it feels like over time we'll kind of follow along the right answer, and that's about as good as we can do, right? And it's kind of dissatisfying. We as computer scientists love optimality, right? We want to be optimal. So isn't there a way we can say, for sure, given what we know here and what we know there, what is the right answer? How can we resolve it to the best estimate humanly possible?